Well, hey everybody, I'm Joe.
I'm Chuck.
And so last year, Michael Keeling and I came to SATURN, and we gave the most amazing talk. And we saw a bunch of the most amazing talks, and we were really excited about all the learning that was happening. And we were also really happy because we knew that back home at Watson, we had left behind just this great piece of code. It was absolutely immaculate. And we were confident that we had left it in the very capable hands of Chuck.
And things were going pretty well. The code was doing well. It's been running in production for a while, no complaints. But then a new feature request came in, and I got assigned to work on it. Uh-oh. It was a very different kind of problem, and it wasn't very clear from the architecture on how to solve this problem. There was some really well-written documentation, and didn't really explain how to solve this problem, and the best people to provide guidance were at SATURN presenting a talk. So, I wasn't really sure how to implement this new feature. I managed to push through it, and I managed to get it implemented to the best of my ability, and I shipped on time. Mission accomplished, right?
So then Michael and I get back from SATURN, and we're super excited to show the office everything that we learned, but first, we need to check all the pull requests that happened while we were gone. And oh my God, Chuck, what did you do to the architecture? This beautiful system that we had built was shattered on the floor. Quality attributes scattered everywhere. Michael had to hold me back from having just a brawl in the office.
That's not what happened.
What could we have possibly done to have prevented this from happening?
I think we could have used architectural hoisting, Joe.
Probably.
Yeah. Before we can get into that, we need to formalize why we're even running into these situations in the first place. The first blow we always encounter seems to be complexity. There it is. Okay. Complexity is a tough problem. If there's anyone in the room who hasn't had to deal with spaghetti code or a ball of mud, we'd like to talk to you after this presentation, because clearly you're doing something really good. However, in most cases, complexity can be solved. There's established patterns and practices that you can use to make the complexity a lot easier.
But even though we can use these patterns to help us guide our development, we work in teams, and we still have to share the knowledge about how we are building these systems with our team members. And sometimes this is very hard because simple things like the team being new to technology or just being up against a hard deadline can cause everybody's internal representation of the architecture just go out of sync. But we usually solve this problem with documentation, right? And our team is actually very good about this. We have services with more lines of Javadoc than code, and we document every architectural decision that we make. So why do we still have a problem?
Well, the big problem for me was that did we go too far? Okay, yeah, and the big problem for us was the fact that, at least for me anyway, was the fact that we were using architecture patterns that I wasn't really familiar with them, and there was nothing in the documentation because it was just inferring that you had already known about them. So it was a general inference problem. How was I supposed to know how things should be done just based on having the necessary context? Another problem that documentation doesn't ensure is developer vigilance. You need to be able to watch out for potential pitfalls when you're working with the code, like making sure you check for certain error cases and whatnot. Without this knowledge, bad things can happen. For example, let's say NASA makes a declaration that everyone should be using Newton meters for their measurements, but some developer who misses the note decides that, I'm going to write this stuff in pound feet instead. Surely the rockets will still work well, right? Or they won't. So, yeah.
So one solution to this problem is to enforce the architectural decisions in your code itself. And that's the term that we call architectural hoisting. And this term was actually coined by the JPL when they were describing the system that they were using to ensure that all their measurements had units that were enforced. And then George Fairbanks later wrote about and popularized this idea a bit. And the key takeaway is that if you use constraints to reduce the space of decisions that your developers have to make, you can guide them towards the decisions that enforce the quality attributes that you want.
What's important is that if you don't have these good guide rails, you can end up in situations where you would fall off the tracks. So what would it look like if we had used architectural hoisting in this problem? Going back to the architecture that I was working with, we were working with what we refer to as the training agent. It is a synchronous data transformation process that uses a pipe and filter architecture written in Go. It takes user-provided training data and puts it through several transformations before passing it off to do more training work. It had been live in production for several months at that point. And just as a quick diagram for people who aren't familiar with pipe and filter, you start from a source, you run it through several filters, and then you get to a sink, which is the end of the program. Here's the main checker go code that we were using for this that uses the pipe and filter. The main takeaways from this is the fact that we, like in this pseudocode, we do a lot of initialization and constructions early on. It's hidden in that ellipses. Each filter runs in its own Go routine, which is effectively the same as like a thread for in Go terms. All these components run in parallel until the end of the pipeline. In order to communicate between these Go routines, we have channels, which is basically a file stream or data stream. And then this is their output, and then we basically just sync all these, we sync all these Go routines together. So for example, the output of a source gets fed into the filter, and then the output of the filter gets fed into the sink. And then the sink is actually what gets returned at the end, and that usually provides some information on whether or not the pipeline had succeeded or not.
All right, so let's look at a few quality attributes we wanted to promote. Since this thing isn't user-facing at all, we actually don't really care about how fast it runs. We just want to make sure we do the correct thing with the data. So obviously, the first thing we care about is testability. And this is dead simple the way we have it set up. Each filter has a single concern, so you just pipe some test data in, and you can validate the output. So it's very simple. We also know that this is a high-touch area where we're going to have to add new filters to create new functionality to deliver like all the sweet AI that we promised our customers. So it needs to be extensible. And this is also just as simple like an insert operation linked list. You change 2 channels around, and as long as the types are correct, it compiles and you're fine. And finally, since it's such a high-touch area, we want to avoid any nasty like worker orchestration or something where we could hide race conditions, because we don't have the budget to debug. But the cool way we set this up is once a filter finishes, its channel closes, it signals to the next filter in the pipe that it's done, and so on and so forth until the program exits. So we avoided any nasty concurrency pitfalls.
Yeah, the code was really nice. Then I worked on it. So for this feature request, I was working on collecting metrics on the overall pipeline. We wanted to collect information that would be useful for us to diagnose issues or see how the pipeline was running. The way I had implemented it, which the formatting is screwed up apparently, is to, instead of extending the pipeline to support these metrics, I instead added a new channel which we call the metrics handler, and which was added to the existing filters. Each of the filters had to be updated to support this new channel and expose information about themselves. And then this is some more pseudocode of the filter themselves, the filter itself. Each filter had to now support this new nosy channel, like having to actually provide the information. Not only that, but like this was sort of boilerplated on, because like even the code was well written. The fact that we even had to like extend everything to add this information, like boilerplated the code and just made things a lot more cluttered. Now each filter had new responsibilities, which required more configuration and more testing, because now it's not only handling the input stream, but it's also having to handle the Zoom metrics module. And this led to some issues with our quality attributes. We now have, like, if we just want to test an individual filter, we have more responsibilities to deal with. Like, for each of the unit tests that we maybe might be using to test the filters, we now have to stand up this metrics module at the same time. Not only that, but this also set a precedent for future features. As it would turn out, this metrics module would set a pattern that would be using for other stuff, such as customer alerts. And if we were using this metric stuff as a precedent, now we have to set up additional channels to do this sort of work. And that actually made testability a lot more harder. Not only do we have to now handle more channels for unit tests, but like we had to update so many more of the existing stuff to use this new channel. Also, there was an issue with extensibility. Writing new filters was a lot more difficult because now we also have, not only do we care about the stuff, like why we're writing the filter in the first place, we also had to, whoever was writing the filter had to have understanding of like, oh, I also need to make sure I set up stuff for customer alerts, I have to set up stuff for metrics. Like all these extra responsibilities that are not related to what the filter is actually trying to do. And just maintainability in general. Like, as we add in more of these type of modules, like it just gets the code becomes more messy, it turns into spaghetti code, This doesn't look like anything I'd actually want to maintain. It terrifies me. I want to run away.
Oh, yeah. Oh,
Sorry, we both did.
Chuck, we got to stop the bleeding right now. This is awful. There's no way that we can get here. How are we going to do this? Well, the very first thing we have to do is just clean up this interface. There's no more funny business. If you're writing a filter, you get one input and you get one output, and that's it. But this alone is not enough, because there was all that setup code in main before where, Chuck could have easily circumvented this, extended stuff in a different way. Mm-hmm. So we want to lock all of that away into a library with a new pipeline abstraction that we'll pull out, right? So that now Chuck will have to go through 2 pull requests to edit the library and the main code if he wants to do something bad. And maybe we'll catch it this time. But this is also where we run into a first problem with the language, is that Go doesn't actually have generics. So in order to pull this setup code up into a library, we actually have to expose some more type information to be able to do the construction of the filters. And so we have to use some big scary reflection, which is kind of silly.
So we managed to hoist the architecture so we could avoid bad situations like this. That's pretty cool. But I'm sure some people are thinking about this right now. Like, okay, so you hoisted it, now what? How do you solve the original problem? Like, we got this really nice hoisted central pipe and filter architecture, but now how were we supposed to be adding in these new modules? We thought about it a little bit, and we noticed like there was a common pattern, and we decided the best solution was to just blend in a common pattern that would support this sort of work. We found that adding a publisher-subscriber model using a message queue was the best solution for this. By adding this message queue, we could introduce the idea of subscribers that can collect information on the pipeline. So they could do stuff like notify issues about problems with training, sending metrics, just any other information about the pipeline that might be valuable. So we extended that interface that Joe just showed to support this new message queue. So now we have this new channel channel called message. And then this message queue would receive events from the individual stages of the pipeline. So this information would be collected. We then added the subscriber interface, which will actually receive the messages on the message queue. So all those individual models you saw before now would implement this interface, and then they would indicate what messages they care about. That way, everything on the all these subscribers only got messages they cared about, and that way we can go from this really messy, ugly thing that could have been the future. Now we have this nice, clean architecture where like everything we need to do to collect information on the pipeline is now fed into a message queue, which gets picked up by these subscribers.
All right, so that was a big case study, basically a whole framework swap. But what are some other ways that you can apply some smaller hoistings that we might care about? So if we also take a look, of course, we support some microservices that have your general 3-tier pattern. And one of the places that we ran into problems was leaking details through our layers from our exceptions. So if you consider I have some business method here that does a database operation. Well, of course, the database operation can fail. And that database exception is an internal detail for this layer, right? So of course, we're going to handle it cleanly, right? Well, yeah, sometimes we don't. So now if we look back up at our API layer, all its responsibility is to interpret the input and call the business layer. But so now what does it do when it gets a database exception that it has no knowledge a database even exists? Well, we don't have enough context to interpret it. So we're just going to guess at what to return. And basically, we ended up shipping API as a random status generator. And our stakeholders were super, super angry at us. So we had to find some way to fix this to make them happy. So basically, we said, all right, well, we're not responsible enough to use exceptions, so we're not going to allow ourselves to use exceptions. So we pulled in a functional library and said, OK, anywhere we use an exception, we'll return an either monad instead. And the beautiful thing about this is that we can force developers to handle errors. For example, when a business method gets a database error, well, it can't just return it because it is not of type business error. And so if we look at our API layer now, it is guaranteed to get businessy type errors that it will know how to handle. And so we no longer have random status generators. But what's important to note here is that this is only enforced by our own vigilance. So if somebody could write an interface incorrectly and circumvent this. But we think we've written it in such a way that a developer will notice that they're doing something wrong here, whereas before they might just accidentally throw an exception.
So now we've cleaned up the exception handling, and the code's a lot more cleaner, so that's really great. But now we've exposed, by lifting up the figurative rock, we've exposed all this excessive defensive programming. It turns out there were a lot more deeper problems than we had originally expected. Here's an example. So in the database layer, we were doing a large number of defensive checks against this data type, which we just call foo. This fragmented a lot of the business logic because honestly, like the database layer shouldn't care about foo stuff. Like this should have been something that had been handled in the business layer. And what happened was we had fragmented business rules like set across all these fragmented rules spread across the architecture. So the database client, the database layer was actually doing all these defensive checks, and honestly, it didn't even have enough context to really diagnose these problems. It was just saying that, like, okay, there's issues with this foo object. We're just going to pass up an exception up a layer. So then the business layer would have to take care of this using this really messy map function that said, like, oh yeah, here's all the possible exceptions that can occur, and then the business code now actually has to infer why these exceptions are happening from the database layer, saying like, hey, I got these exceptions, I got to figure out why this is failing when it already had the context to begin with because it passed information down to the database layer. So the way this could be solved is by doing some forced validation, and we're talking about doing it here with type systems. So what's being actually fed into the database layer now is a valid foo object. So it implies that we've done some validation up front, and now the database layer says like, okay, I only care about the stuff that's actually relevant to me, and I don't have to do all these excessive defensive checks. We can take that, no defensiveness is actually required anymore. And then we have this now validate foo method that will actually get called by the business layer. So now the business layer calls this validated foo, gets a valid foo object which gets fed into the database layer. We can actually take this a step further because to make sure that only the business layer actually calls this method, we end up giving the validated foo method a return object of either business layer of a business layer object. We can't actually call this in the database layer because the database layer returns a database error. So like the only place where this validated foo method can get called is in the business layer because that's the only part that actually returns a business error. So a little more enforcing there.
All right, so these are all like real cool things to do, but how do we actually make time in our daily work to do this? If you remember, we had this big pile of spaghetti, and we came up with some really strong ways to hoist it away. But as it turns out, this was actually one of our largest code bases. And hoisting these things was going to be a massive undertaking. And when we sat down and did the estimation, we realized that it would take 4 months of not shipping value to swap everything over. And we could not take this to our project manager. He absolutely would not allow that to happen.
Yeah, he wouldn't let us halt production on new features just to do this refactor.
So how do we do this, Chuck?
So we used an approach which we've been calling tracer missiles. Not literally these kind of missiles. But the idea is that, like, this is sort of an extension on the idea of doing tracer bullets, which is where you build a minimum implementation of something while you're testing out new tech. We're doing the same idea here, but instead of doing a minimal implementation, we're actually doing full features, bringing over any of the old code and support that we need along the way. So it's sort of like a bigger payload. The way we actually implemented this idea was that we actually stopped doing work on the old architecture, and we actually stood up a second deployment of our code using the new architecture. Using this new architecture, any new features that we had to implement, any new value was done on the new architecture, and the old architecture was left alone. If there was any point in time where we needed filters from the old architecture, we actually took the time to port those over into the new architecture. And by doing things in this way, we were able to slowly migrate all the old architecture over. Eventually, we got to the point where we were, before I get that, there were some cons to this method. The two big things we had to deal with was, one, we had to do the overhead. Like, it wasn't as simple as just implementing a new feature. We actually had to port code along the way, which took some time. Another issue is because the old architecture is still in production, we had to deal with any sort of bug fixes that may have come along. So whenever there was like a new bug for whatever reason, we actually had to update two architectures to make it happen. But I mean, 6 months later, like after doing this process for a while, we were eventually able to get to the point where it would take 1 month to port over the rest of the code. And by then, we were able to talk with our product manager, and he said, yeah, like we can spend a month to finish this off, and then we can retire the old architecture entirely.
All right, so if you didn't take anything away from this talk, the most important thing you should remember is architectural hoisting is a great way to enforce quality attributes while you're away at conferences, like right now.
Right now.
Okay, so some key questions. When should you try to do some hoisting? Well, our favorite strategy is to check if everybody who works on the code can actually draw the architecture. Because if nobody can get a coherent internal representation together, then obviously you have some problems that you should deal with.
Oh, another thing you should be looking for is poorly defined system boundaries. So using this example from before, we shouldn't be leaking like exceptions from different layers into, like for example, database exceptions into the business layer. If you're seeing this kind of work being committed to the code, it's likely that there's people who don't understand how the architecture works because they're leaking all these exceptions around, and you should probably look into doing some form of hoisting to prevent this from happening.
And finally, you should look around for some late binding assumptions. So like we saw before, if you have like all these excessive defensive checks that don't really make sense in the context that they're in, and then your error handling doesn't really make sense either, then you should probably have some constraints to force your developers to go in the right direction.
So how should you hoist? The first thing we suggest is refactoring the architecture.
I didn't do it.
No one saw anything. The first thing you should do is refactor your architecture as you go. Like, don't wait till it gets into like a terrible, terrible state. We found that like if you can start refactoring code along the way now, you'll pay off in the long run. Otherwise, you could end up in a situation like we have, where we've had to actually rewrite 2 services because it's gone so bad. The next thing we should look into is using tracer missiles. You're going to need to be, it may be necessary to get creative with like the way you do your hoisting. So you might have to do things like in a non-traditional way to make it happen, but just make sure you have some sort of plan rather than just arbitrarily doing some form of hoisting. The last thing you should keep in mind is being intentional. You need to understand that, like, you know, ask the question of like saying, is this something that we need to hoist? It's very much possible to do hoisting incorrectly and actually make things painful for yourself. So like you need to say like, is this something that will actually help things in the long run? And it may be necessary to say like, okay, well, we're not going to hoist this and we're just going to accept the tech debt.
And finally, what are some things you should avoid? Well, definitely the second system effect is bad. You should focus on the one quality attribute that you're trying to promote when you're doing a hoisting, because other changes can always come later. Second, avoid the urge to stop documenting. Like, this isn't Agile round 2. If the developers don't have the context for the guide rails that you built in, they might try to reverse them anyway. And finally, don't hoist everything up front. You're encoding design decisions, and just as you wouldn't make all your design decisions up front, you know, we would have failed if we had tried to do these things beforehand. And anyway, so we left this guy in charge of the code while we're here today. So you can come back next year to see how he broke the architecture during this talk. Thank you.
So that's it. We've been obligated to say that Michael Keeling has written the book and that you should totally check it out. So.
So if I have questions, if anyone has a few questions.
So did you have any challenges with when you were doing the hoisting because your feature estimates increased as you were doing the hoisting as well as the implementing the new feature?
Yeah.
Oh, yeah, definitely.
That definitely happened. I mean, obviously we were working at a slower pace because we were doing this extra work.